Okay, so with this lecture, what we're going to discuss is how the Navier-Stokes equations are used in practice. Okay, because in general, the Navier-Stokes equations are horribly nonlinear. Partial differential equations. In fact, they're so difficult that they're the subject of movies. For instance, there's a recent movie with Matthew McConaughey in it where an element of that movie is the fact that his sister solved an enormous challenge for the Navier-Stokes equations that that is currently unsolved. And what Matthew McConaughey's sister solved in that movie was she proved existence and uniqueness for Navier-Stokes. But in reality, these equations are so complicated that existence and uniqueness of the solutions has not been proved. Okay, and what I mean by this, and that's even in the arguably simpler incompressible case where we're solving grad v, or the divergence of the velocities equals 0, and rho dv dt equals minus grad p plus mu del squared v. and that's even ignoring gravity and things like that. So just solving these equations here is extremely challenging. And in general, and again, as it's so difficult that even a basic property that if you have a solution to the Navier-Stokes equations, is that solution unique, and under what conditions is a valid solution to the Navier-Stokes equations even valid? That basic question has not been answered, and if you can answer that question, that is one of a number of $1 million math prizes. So if you could prove this for Navier-Stokes, you get $1 million. Okay, and there are exact solutions to it for very simple cases. You can solve the Navier-Stokes equations exactly. And we will do this for a simple case in Chapter 8. Okay, and that involves pipe flow. Okay, and now that does not mean that we went through the trouble to derive these equations and to show them to you. That does not mean that they're completely useless. And I'm just showing you guys this stuff because I'm mean and hard. No, these are extremely useful in practice. And where they're useful is other times you use a computational fluid dynamics. Which is given the acronym CFD, which I'm sure at least some of you have heard of in this class. And there are two basic approaches. And so with CFD, what you do, so say you have a complicated flow, and you want to study how the flow goes over and around, I don't know, this circle here. Okay, there's going to be a very complicated flow pattern. As the streamlines go over and around this object, you'll have a circular flow a pair of counter rotating vortices here and here, depending on how fast the the flow is here. Now, for this case here that I have sketched here, there is no exact solution to the Navier-Stokes equations for that. It is just way too complicated. And so, but a case like this for modern computing techniques is actually very, very simple to do. And so how do we actually solve these in practice? So first I'm going to make a copy of this and stash one for later. Okay, well, there's one technique. There are two basic techniques for solving computational fluid dynamics. There are two key ones. One is called finite difference. And with a finite difference, you approximate the partial differential equations directly. Okay, and so, for example, with finite difference, what you do then is you define a computational domain, and you basically seed it with a whole bunch of points that I'm drawing here. Okay, oops, get that one, get rid of that one. And you have these points here. And basically what you want is you want the solution to the Navier-Stokes equations at each of these points here. And so how do we do that? Well, I'm going to label this point here as ij. This point here is I minus 1, j. This point here is I plus 1, comma, j. And basically this ij numbering is the traditional numbering for points. So the x coordinate, so this here, I is the x coordinate of this point here, I plus 1, oops, wrong way. I is the coordinate of this point here, I plus 1 is the numbering index of the next point. And these points are spaced delta x apart and delta y apart in height. Okay? And so say at this point here, we want to solve the Navier-Stokes equations, and we want to approximate the quantity u times partial u partial x at point I, j. Well, how do we do that? Well, here you use techniques from your numerical methods course that you may or may not have taken, and you approximate this as, and there are lots of ways of doing this, as u ij at that, which means u, so u ij means u at this point here, times an approximation of this derivative here. And for those of you who have had numerical methods, you would know that basically one way of approximating this derivative would be u of I plus 1 j minus u of I minus 1 j divided by 2 delta x. Okay? And so this here is u, and this here is approximately partial u partial x. And so with finite difference, you just basically lay up a grid of points, and then basically using the data that is at each of these points, you then go and approximate all the terms in the Navier-Stokes equations directly, and then just solve. Now, there are a lot of games you have to play, and there are a lot of other details. But that's the basic gist behind the finite difference technique. Okay, and now the other technique that you'll see used quite a bit is called finite volume. Okay, and the other technique, as I said, is finite volume. Okay, and now the main difference between finite volume and finite difference is finite volume, and I'll just call this FV. FV uses the integral form of the conservation laws. Okay, and so what you do here then is for finite volume, instead of dividing the domain into a bunch of points, you divide the domain into a bunch of finite sized control volumes. Okay, and so whereas for finite difference, we had a bunch of grid points here, here, and here, with finite volume, what you do is we actually draw a grid, and I'll just draw a few of the points here, and these are all little control volumes. So these are finite control volumes. And so with finite volume then, rather than working with the differential form of the Navier-Stokes equations directly, is that we do not start from here as we did with finite difference. Instead, we start with the integral form of the conservation laws. And so, say for example, we zoom in onto this finite volume here. I know this is starting to look messy, just please bear with me. And so we have a control volume that looks like this, and I'm going to draw its neighbors to the top and its neighbors to the right, the neighbor to the left, and the neighbor to the bottom. Okay, and this is the center of that computational finite volume. And in finite volume, the control volumes are often called computational cells or just cells. So if you listen carefully to my lecture when I was deriving Navier-Stokes, the finite control volume, I often accidentally called it a cell because I'm so used to working with finite volume in my own research. Okay, and so again, we basically label the cells with a numbering system. So I is an indicator of the x position of the cell, and j is an indicator of the y position of the cell. Okay, and so this would be the cell center right there. And then we also define points on the midpoints of each, on the edge of each computational cell. And this would be point I, j plus 1/2, because we are going up by a distance of 1/2. And the height here would be delta y, and the width would be delta x. Okay, and the point here would be I plus 1/2 j. The point here would be I, j minus 1/2, and the point here on the edge would be I minus 1/2 j. Okay, and so and then all these edges here are called cell faces. And I think you can kind of see where we're going with this. Is that we basically use the integral form or the Reynolds transport form or the Reynolds transport theorem form of the conservation laws directly. So suppose we want to do a conservation of mass. Okay, well, with the finite volume, we use the integral form or partial t, the integral over the control volume rho dv, plus the surface integral of rho v dot n hat dA, and that's equal to 0. So for finite volume, we start from here. We start from the fundamental conservation law itself. And essentially, you do the same thing that you have always done. Okay, and now we need to approximate all of these integrals here, and we're going to do it the exact same way that we did for the infinitesimal control volume. We're going to use the midpoint rule. So use the midpoint rule. Okay, and that means that the volume integral of rho dv is approximately rho at ij delta x delta y. Okay, and now note, since delta x and delta y are not approaching 0, there is some error. Okay, so unlike for the finite control volume, this approximation is not exact because delta x and delta y are not approaching 0. Okay, and then you do the same thing for the integral of the surface forces, and here's where the error really comes into play. So the integral of the control surface rho v dot n hat dA, and I'm just going to cut right to the chase. This will equal to delta y, and again, you just walk around the control volume. You guys have done this about a bajillion times, times rho u at I plus 1/2 j minus delta y rho u at I minus 1/2 j plus delta x rho v at I j plus 1/2 minus delta x rho v at I j minus 1/2. And so now the trick here is that we need to approximate the mass flux, or rho u, at all of these edges of the control volume here. And there are lots of ways of doing that. Okay? So you can do a Taylor series. But because delta x and delta y do not approach 0, higher order terms that are neglected introduce error. Okay, and so obviously the more terms you take in the Taylor series, so you could say f at position x plus delta x is approximately equal to f plus delta x partial f partial x plus delta x squared over 2 factorial partial squared f partial x squared plus delta x cubed over 3 factorial partial cubed f partial x cubed, and so on. So with finite volume, you can use Taylor series to approximate these values at the edge of each control volume. But because delta x does not approach 0, these higher order terms here actually contribute. And so there's a lot of games you have to play with approximating these edge fluxes. Okay, but again, the moral of the story here is that with finite volume, you basically do exactly what you did for about the past 6 weeks. Is you just use the integral form of your conservation laws, could be mass, momentum, or energy, and you walk around the control volume. You form the time derivative term and the flux term, and then for a momentum, you may have to walk around the control volume and find all the pressure forces and viscous stresses, etc. But it's very analogous to everything that you've been doing for about 5 or 6 weeks now. And but what makes finite volume hard is approximating the values at each edge of the control volume. Okay, and there are a lot of ways of doing that, and we're not going to get into that in this class. But I will show you some examples of CFD in the finite volume method and how that works in our group. So here's slideshow, play from current. So here I'm just going to show a movie of a CFD calculation. Over here, we're just simulating an explosion and a layer of reactive gas. So we're solving fully compressible Navier-Stokes equations with combustion reactions. Okay, so I'm just going to let the movie go. This will look crazy, but it should be pretty interesting. And so what we do with this calculation is this is massively compressible. And one thing to notice too is that even though we didn't start with a spinning fluid, you see all these regions of fluid here that's spinning. And so there's a massive, so there are a bunch of little vortexes, and there's a massive amount of spinning fluid or vorticity here. And I'll play the movie again. And this structure over here, that's called a shock wave. In front of it, there is no flow, and behind it, there is a massive flow that is going into it. So there is a massive amount of velocity divergence. And so the key thing is that a lot of the physics, a lot of the basic science and principles that you guys have been learning in this class were actually applied to solve these equations. Oops. Okay, and so slideshow. Okay, and so now I'm going to explain briefly how this was done. So here we have a similar computation, but of a slightly different scenario. Here we're showing the full computational domain, and so this is the entire calculation. And this little region here is where all the action is, and I have a zoom in of that. And so we can see all the full detail that is going on. And so now the question is how do we do that? Well, this code uses the finite volume method. So we took this entire computational domain and we chopped it into a bunch of little control volumes. So each one of these little squares that you see in here is its own finite size control volume. In our particular code, you can change the size of the finite control volumes in different regions. So this completely black region here is just a very fine nesting of control volumes. Okay, so I'm going to go to the next slide. And so we zoom in close to the action, and you can see that there's even more, that the number of or that the size of the finite control volumes gets smaller. I'm going to zoom in more, and this is close to the front of the main action here. And so you're starting to see that we're seeing progressively smaller and smaller squares. And the reason that we make the finite control volume smaller and smaller and smaller is that the error introduced is a function of delta x and delta y. And the smaller delta x and delta y are, the more accurate the computation is. But the larger number of control volumes you have, then the more expensive the calculation gets. Okay, and we're zooming in more, getting closer and closer to the action. So here you're starting to be able to see all of the individual little control volumes. And so we're going to zoom into this region again. And now you're starting to see all the individual control volumes. So zooming in even more, now I'm going to zoom into an even crazier amount here. And so now all of these little squares here that you see is its own computational control volume. And essentially what the code does is it computes the flux on this cell edge here, 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 and for conservation of mass, it just walks around the control volume and solves partial t, the integral over the control volume rho dv, plus the surface integral of rho v dot n hat dA is equal to 0. And it does the same thing for conservation of mass and for conservation of momentum and conservation of energy. But still, the basic principles that you guys have learned are at play in these CFD codes. Okay, and so that's it for that, you guys. For those of you who will work with fluid mechanics, you will more than likely use the CFD codes such as OpenFOAM or Fluent or StarCD or CFX. And most of those codes, as far as I'm aware, they are based off of the finite volume technique. Because to us engineers, after we get used to control volumes, the finite volume technique is so intuitive to us. You just define a bunch of little control volumes and walk around them and compute the fluxes going in and out of them, going in and out of the surface. And that's basically how that works in a nutshell. Now, let's gonna do a little bit of a tangent here, but say you're in a design scenario where you need to optimize something. And you need, oops, sorry for scrolling the screen down, to optimize. Full-on CFD is too expensive for that application. This sometimes literally takes thousands of CPUs, multiple days to complete. In my own research, I've done CFD calculations that have required 30,000 processors on the order of 2 or 3 days to complete. So CFD calculations can get very, very large. I believe the CFD calculation that I showed you, that used on the order of 512 processors for about 10 or 12 hours. So these are very expensive things. So if you're trying to optimize a design where you need to go through an iterative process and potentially solve hundreds upon hundreds of CFD calculations, that's just not practical. However, sometimes in these optimization scenarios, the integral form, just drawing a giant control volume around the whole object that you're trying to optimize, does not provide enough information. Okay, so essentially a CFD has TMI, or too much information sometimes, and hence it's too expensive. And the integral form, where you have some gizmo, say some goofy gizmo, and you want to calculate and you want to know the details of what's going on, if you just draw a giant control volume around the whole thing, well, that may not be enough information. So is there something in between that you can do? In certain scenarios, the answer to that is yes. So is there an in between? And the answer is yes, but not always. Okay, and you will, and as you guys get experienced with design, or you become experienced engineers, you will learn basically when you can use the sort of techniques that I'm going to show in the next, let's say, 10 minutes. So I'm just going to show this by way of example. So example. So say we have a tube that's blocked on one end, and we have a tube here of diameter d. Okay, and this tube is porous. And say, and it's of length L, and we're defining x from the closed wall. Okay, and now this tube is porous, and say it could be like a piece of drainage pipe in your yard or something like that. And say around the circumference of the pipe, we have a uniform flow going into the pipe from the surface at velocity vf. Okay, and as a result of this flow going into the pipe at velocity vf, we're going to have a free jet of fluid exiting the pipe, and that will be leaving at velocity v. And so say you are tasked with optimizing vf and the pipe diameter and the pipe length. And to do that, as part of it, you need to know what is the mean velocity in the tube as a function of x, and you want to make sure that this pipe doesn't burst, so what is the pressure in the pipe as a function of x? And so this is a scenario where the integral form does not give the required u of x or p of x. Okay? And CFD is way too expensive for this scenario. Okay, and so basically it'd be complete overkill to use CFD for such a fairly simple case like this. And so, and you're tasked with optimizing the various design parameters. And so one approach, there are lots of approaches for doing this. So say you want to find u of x. Well, first you lay out your assumptions. And so we're going to assume steady flow and uniform flow. Right? So in this case, we are only concerned with that each position, at each position on x, we are only concerned with what is the average velocity across the tube at that given position. We don't care about the variation of that velocity profile. We just want to know what the average velocity profile is. And so how do we go about doing that? And finding its position. And of course, we'll assume incompressible flow. And so our approach is to use an infinitesimal control volume, but rather than dividing it into a bunch of tiny, tiny little squares, we are going to divide it into a bunch of tiny little disks. And so we're going to assume a one-dimensional uniform flow. And we're going to use a disk-shaped control volume. Okay, and so here, what I mean by that is I'm going to redraw the tube. And we have the tube of length L. And so at position X, we're just going to draw a very thin pancake-shaped control volume. Okay? And on this control volume, which is at the center of it, is at position X. And the thickness of the control volume is, you guessed it, delta X. And at the top of the control volume, or around the circumference actually, we have fluid velocity Vf going in. And at the center of the edge here, we have I hat, the normal vector is I hat, and we'll have some velocity u at x plus delta x over 2. And you guys should be pretty experienced with that delta x over 2. And going in from the left, we have u at x minus delta x over 2. And we have minus I hat pointing to the left. And so now on this disk-shaped control volume that I have here, we apply conservation of mass and momentum, and possibly energy if you need it, just like we always have. And so first we're going to find the velocity as a function of x. So apply the integral form of the conservation laws to the disk-shaped control volume. And so I'll show you how to use conservation of mass. And for a homework problem for this, you will apply conservation of momentum, neglecting shear stress at the wall to find the pressure as a function of x. Okay, but as an example, I'm going to use do conservation of mass for you. So conservation of mass. And that's the same as always. So that's partial t, the integral of the control volume of rho dv, plus the integral through the control surface of rho v dot n hat dA is equal to 0. Well, we're assuming it's steady, so the time derivative goes to 0. And then you can, because of that, because we're assuming incompressible flow, rho is equal to constant, which implies, as usual, that we get the integral over the control surface of v dot n hat dA is equal to 0. And so I'm going to redraw the control volume to be a little bit bigger. So we have the control volume looking like this. Okay, and we have Vf going in through the circumference. The width here is delta x. We have minus I hat, plus I hat here, and at the center we have the mean velocity, and I'll call that u at x plus delta x over 2, and u at x minus delta x over 2. Okay, and actually, technically I should call this v, but I'm going to call this surface 1. This is surface 2, and the outer circumference is surface 3. Okay. And for area 1, we have the disk, I hat, and u at x plus delta x over 2. And then v dot n hat equals u at x plus delta x over 2. Okay, because the velocity vector is u I hat at x plus delta x over 2. And n hat is I hat. Okay, so you can take the dot product we can take the dot product of velocity vector and I hat, and you get u at x plus delta x over 2. Okay, then we're assuming uniform flow, so the integral over a1 v dot n hat dA1 equals v dot n hat a1, and our a1, which is located at x plus delta x over 2, and a is pi over 4 d squared. Okay, and this here is u at x plus delta x over 2, and so this whole thing equals pi over 4 d squared u at x plus delta x over 2. Okay. Then for area 2, where we have the left circle, that's minus I hat, and we have u going in at x minus delta x over 2, and v dot n hat in this case equals minus u at x minus delta x over 2. Then the integral over area 2 v dot n hat dA2, you can go through the exact same procedure. That will equal to minus pi over 4 d squared u at x minus delta x over 2. Okay. Then area 3. Now, normally for most of our other problems, area 3 would have no contribution. But here we have a porous tube, and there's some mass coming in through the outer circumference, or through the wall of the pipe. Okay, so we have VF. And this is of width delta x. Okay, and I'm just going to call this n hat 3. Okay, and V3 equals minus VF n hat 3, because a VF is going in the exact opposite direction of n hat 3, which implies that V3 dot n hat 3 equals minus VF, and VF is just the velocity of the fluid going into the pipe through the wall. Okay. Then the integral over a3 v dot n hat dA3, that equals v dot n hat a3, and we don't have any. This is at x, so no subscript. Okay, and so this equals v dot n hat a3, and a3 is around the circumference of this shaped, and so that area is pi d times delta x, and this is minus VF. Okay, and so the integral of that is just equal to minus VF pi d delta x. Okay, so now we know all we now know all surfaces of the control volume. So now we just put everything together. And that means the integral of the control surface of v dot n hat dA is equal to 0. And we add the contribution from area 1, that's pi over 4 d squared, which is just the disk area, times the mean velocity leaving through that disk, and that's given by u at x plus delta x over 2, plus the contribution from area 2, which is negative pi over 4 d squared, times u at x minus delta x over 2, plus the contribution for the mass coming in through the circumference of the circle, and that is equal to minus delta x pi d, pi d vf. I tapped the up button and it moved up a page. Sorry about that. Okay, and this is equal to 0. Okay, and so I'm just going to do some light rearranging here. This implies that pi over 4 d squared times u at x plus delta x over 2 minus u at x minus delta x over 2 minus delta x pi d vf is equal to 0. And now we're going to take the limit as delta x goes to 0. Oops. But before we do that, I can do some simplification. I have pi here, I have 1d here, and I have 2d's here, so I'm just going to cross out the square. Okay, and then I'm going to use the Taylor series on this. This would be u plus delta x over 2 du dx. And notice here I don't have partial derivatives because in this case u can only be a function of x. And then the Taylor series for here would give u minus delta x over 2 du dx. Okay. So we combine those two terms, and then you would minus, the u cancels out, and this just equals delta x du dx. So, substituting that in, we have d over 4 times delta x du dx minus delta x vf is equal to 0. Well, there's a delta x on both sides. And we can rearrange this into du dx equals 4 vf over the pipe diameter. So now we have an ODE, or an ordinary differential equation, that you can solve to find u of x. Okay, and this can be solved to find u of x. Okay, and so essentially this is a pretty straightforward one because this is just a constant. We're assuming that vf is not equal to a function of x, and so this is a first order separable ODE, and we can solve that by just multiplying both sides by dx, and then you get du equals 4 vf over d dx, and we can integrate this, and you get u equals the integral of 4 vf over d dx from 0 to the end of our tube, actually from 0 to x, sorry about that, plus some constant. Okay, and for this problem, these are just constants. but in industry, VF may be a function of X, and you will actually have to integrate it. Or if this ODE is too challenging to solve by hand, you may have to use something like MATLAB to solve those ODEs for you. Okay, and so we do this integration, and this implies that u of x equals 4 VF over d x plus the integration constant. So how do we find the integration constant? Well, we only have one constant, and so we need to know the velocity u of x at one position to be able to solve this. But at the left side of the tube, this is an impermeable wall. Okay, and flow cannot penetrate this wall over here. Okay, so flow cannot go through this wall. So in other words, if this wall is stationary, u at 0, because the flow can't go through it, is equal to 0. Okay, and this is called a boundary condition. Okay, which basically means to specify the exact function of x, you need to know at least one detail about u somewhere in the basically at some location in the tube. And fortunately for here, we know that the flow velocity must be 0. That the mean velocity of the flow must be 0 on this end of the tube. So then, to find the constant, apply the boundary condition. That u of 0 equals 0, and here we just set x equals 0 into our result here, and so you get 4 times VF over D times 0 plus C0. Well, immediately we can now solve for C0. This implies that C0 equals 0. Okay, so then finally, u of x, which is what we were after, is given by the function 4 VF over the pipe diameter times x. And for part of your homework, you guys will work with conservation of momentum to find P of x. Okay, and here you need to think about the boundary condition and how I very carefully labeled the free jet that's leaving the end of the tube. And that will tell you your boundary condition. So in that case, you will know P at the end of the tube, which is length L. You will not know it. At x equals to 0. And so I'm going to end the lecture here. This is a bit of a long one, but now we're done with differential analysis.